Okay, welcome to Bio 347. This is lecture 3, the nature of data, and this is part 2, where we're going to look at the experimental unit, randomization or not. All right, let's get to it. So the experimental unit. So this is a subtle but important thing to understand about collecting data. So let's say you are sampling plant diversity and you have this really big field and half of it was burned. Okay. And what you do is you're going to put down a quadrat, 1 meter by 1 meter quadrat, and you're going to pair them up. Okay, so you have a bunch of pairs across your samples, across your fields. Okay, so you're interested in diversity, right? And how burning affects diversity. And what you would hope to do eventually is to say the effect of burning on diversity. So whatever we measure, there's going to be an average and then the effect of burning. Okay, so you want to know this, but you have to know your experimental unit because you have a sample, right? So 2 samples in a plot. Okay, let's do this. So we can say these are our plots. And we can make them, let's make them circular. Right? So we have our samples within our plots and 2 plots per sample. And then we have our samples within a field. And this side will affect what goes on this side and will affect your statistics and what you can say about things. So if you want to know about your sample, right, then you have to know about your plot plus burning. Okay. If you want to say, well, let's just say at the level of the plot, diversity at the level of the plot, right? Then that's going to equal burning. All right, but here's the thing. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. You have 14 plots. Let's put that here, 14 samples, sorry. And then 3, 4, 7, and then 2 fields, okay? So you have a lot of samples, fewer plots, and only 2 fields. So the thing is, you may not be able to say much about burning because you only have one burned site, okay? So your level of inference is going to change depending on what level is your experimental unit you want to say things at. So I just ran into this analyzing my own data, okay? And here's why. Whoop, that is not what I wanted to draw. You have oak trees, and we collected hundreds of acorns per tree, right? So acorns and acorns and acorns and acorns, acorns and acorns and acorns, acorns and acorns, and lots of students cutting open acorns and looking for weevils. And here's the thing. If you looked at, say, 100 acorns and 100 acorns, you still only have 2 trees. Okay, so what you have to ask yourself is, how many acorns do you need to sample until you can say something about this tree, right? Because you could always sample more, and if you're busy sampling acorns, you're not busy sampling trees. Okay, so what you want to do is find that balance between sampling the subsamples in your samples to say something about whatever, right? If you want to say something about acorns, maybe you want more acorns. You want to say something about the tree level, and you need more trees, right? Maybe fewer acorns per tree, right? And then how representative are these acorns of the whole, right? So these are all things you have to understand when you're running an experiment. Okay. Pooling data. So here's something I did. Some data I collected. I'm just going to draw eggs, even though we're actually looking at chicks. Okay, so I had a whole bunch of nests, and when these hatched, I looked at the blueness of the feathers. So you put it under, you use a speck, you shine a pen on it, you get some measure. And here's the thing. You have one mother feeding these and a mother feeding these. So there's going to be a nest effect. So the question is, do I pool or not? By pooling, it means we have one sample. If we don't pool, we have 5. If we pool, we have one sample. If we don't, we have 4. Okay, so it's even more complicated than that, because what you might have is, say, 2 males. Oh, I need to add in 1 to make it 5. You may have half of them be males and half of them be females. So we could pool these males together, right? So we could have 1 nest. We could have 2 pool together, these 2 or these 3, or we have 5 if you count for individuals, right? So these are all things I had to figure out when you go to analyze your data, because you have to count for the fact that these are not independent, and we'll get to what that means. So by pooling, what that means is you collapse levels. So we have gender within the nest, we can collapse by that, or we can collapse by the whole thing and ignore that there's 5 eggs and just say take an average of the color of these birds, right? So the advantages to pooling is that it makes it much simpler, but the disadvantage is that you're going to miss some things, right? So you lose information when you pool, but you gain other things. So you gain simplicity. All right, randomization. So let's go back to our field. This is not what I wanted to do. There we go. All right, there's our north arrow, right? And we had burning and then unburned. And we could have sampled one of 2 ways. So what we'll do is we'll break this up in half. All right, let's try this again. Burn and control. And we're going to split this up. And we're going to have systematic sampling and then random sampling. So systematic sampling is really straightforward. You're going to say, we're going to pick, we're going to walk every 10 meters, take a plant sample, walk 10 meters, take a plant sample, walk 10 meters, walk 10 meters, right? And then we'll end up, make this 100 meters apart. So we end up with these two things here. That's systematic sampling, okay? Randomization means that you randomly sample and one sample's location is not influenced by another, okay? And by the way, you know, how would you do this? Now in this one, you get out a 10-meter tape and you pull it, lay down a sample, pull it, lay down a sample. How would you set it up randomly here? I would do it by considering this X and Y coordinates from 0 to whatever this is in meters, 0 to whatever this is in meters. And if you want 20 samples, just generate a random X and a random Y. Go to that point, boop, take it a little bit longer, but it'll be random. So what you end up is sort of like this, right? It's not truly random. By the way, random is really hard to do when you're a human, right? So what I'm showing you is what might appear to be random, but what it is actually arbitrary. So there's a difference between what's arbitrary and what's random. Random means there's a process that generates it. It's not systematic, it's actually random. Arbitrary means that there's just some point you pick, right? It's not based on anything that you're conscious of, but there's probably an unconscious selection going on. All right, so let's say this is your field that you sampled, and you want to know the difference between these control and burn plots. Let's say that the farmer had two roads, and his roads went like this. One went through here, and the other went through here. If you want to know, and the roads are just part of the landscape, right? So they're part of what you want to know. By not having random samples, you never know, and you never sample what's happening here, right? Through systematic sampling. But the random sample gets samples here and here and here and here and here, right? As well as those off the road. So by random sampling, you get a better idea of what's happening. Everybody thinks that systematic sampling is the way to go. It's actually random sampling. It's the way to go. Okay? So the error induced is actually taken account for when you do random sampling as opposed to systematic sampling. Okay. So that's randomization versus systematic sampling. All right. IID, what is that? IID is independent and identically distributed. Okay. And what does this mean? So independent means that your samples have no influence on each other, right? And let's go ahead and break that. So you are looking at stress in kids going to the dentist, right? And one kid goes in and he hears the kid in the room being very uncomfortable. So the kid's crying, and that means this kid is going to go in. Oh, that kid. He's a giant kid with a giant head. He's going to go into the dentist's office already nervous, right? Because this kid is influencing these kids. So they are not independent, right? So if you wanted them to be independent, what you would do is put up a wall where they can't see each other. This kid, he cries. This kid doesn't hear anything. And he doesn't have the same experience. So he ends up turning his frown into big smiles, and he gets a lollipop, right? Sugar-free lollipop, which he then throws on the ground because it tastes horrible. All right. So that's independent, right? Independent means your samples aren't affecting each other. And I'll go into this more in detail. Identically distributed is a little bit more difficult to explain. Okay? So what that means is you're sampling from the same population, but getting different levels. Okay, so for example, you're interested in the swim speed of some centimeters per minute, and this, say it's like this, and we're looking at temperature, and you'll get points like this. Without the lines. Right. And even if you look at a particular temperature, right? Let's just keep adding so this makes more sense. You sample lots and lots of tadpoles. Okay. If you look within any sample here, what you'll find is some sort of distribution like this, right? Where you're assuming these are all from the same distribution, right? And they're all from the same population. What you don't want is something like this, and this thing is actually, for whatever reason, doing something very different, right? So it would be shifted over, and that's what's causing this. It's not the effect of temperature, it's some other reason that you're not catching, right? And if you were to put this guy back at this temperature, right, and when it go down, it might do something else. So what you assume is all these points along this line at any temperature, right? So within a temperature, then among temperatures, they're all kind of from the same population. There's not some strange thing like you're missing, like if you think you have a bunch of bullfrogs and then you accidentally had some other frog in there whose tadpoles act very differently, they would not be identically distributed, right? So that's what that means. It's just one of the assumptions is that, you know, everything is the same. The experiment would work the same over and over again. You get the same distribution for, if you were to select another 100 bullfrogs, you wouldn't get the same points at the same place, but you'll get the same line, essentially. All right. Again, being independent means that your tadpoles aren't affecting each other, so they're not chasing each other, something like that. All right. Autocorrelation is when you break this IID assumption. So you can have spatial, I'm sure there's more, spatial and temporal. Auto correlation. So the example I gave with the kid is temporal correlation. Because let's take a series of kids that go into the office. And let's say there's no way to put up a barrier. One kid waits while one kid gets a dentist. He leaves, another kid could go in the waiting room. So this kid influences this kid. This kid influences this kid, and so on, right? So this is simple one-step correlation. If you had two-step correlation, what that means is you would actually have something like this, right? And those situations do arrive. Most of the time, you just have simple one-step correlations where one sample affects another one's. And these kids are different. A lot of times in temporal autocorrelation it's because you're sampling close together in time. So let's say you're looking at a weight loss program and it works, but it takes a while. So if you were to sample within here, very close in time, you wouldn't see any effects. And here, because of autocorrelation, your weight the time before, at any time, is very close to the weight you were just before that. If you were to space them out, right, then they're less affected, okay, as opposed to when they're close by. So that's temporal. Spatial, okay, spatial autocorrelation arises, right? We have our field, we split it, burn, control, and we did a good job of randomizing it. But realize that these two are close in space, so the variations in soil, or maybe, a herd of deer came through and ate these grasses all the way down. So you would find that these two will behave, in what you're measuring, they'll behave more closely because they're close together in space, as opposed to points that are farther apart that have different soils and different histories. Okay, so, and then of course there's space-time, in which case a lot of health data has spatial temporal autocorrelations. So if you, for example, if you look at a city and look at health, that people that live close to each other will have similar health histories. And if you were to follow them through time, that, because of, let's say, air pollution and whatnot, that they'll act much more the same together through time than somebody that lives more rurally may be different. So you can have spatial autocorrelation, temporal, and space-time autocorrelation. Sounds like a science. It just means that your samples are affecting each other. That's the takeaway. Your samples are not independent. They're actually affecting each other. All right, pseudo-replication you see with pseudo-replication. So pseudo means false and replication. we have our field, right? Burn control, and we could do 1,000 samples. I'm not gonna draw 1,000 dots, right? But each one of these is a meter plot, right? And then the question is, how many samples do we have? Do we have 2,000 or 2? Because we want to say something about burning. We have a field that is burned and a field that is unburned. So technically, we only have 2 fields. And technically, we only have 1 of each, right? So if you were to consider all these samples, right, within these fields to be actual independent samples, then you would be committing pseudo-replication, okay? And the same thing, let's say you want to know the diet of people, so you follow one person and you watch them eat 100 meals, your sample is still only 1. And so pseudo-replication can be done out of ignorance, and it can be done maliciously. If you put in your methods that you committed pseudo-replication, you say, like, this is what we did, that's a lot more forgivable than saying you collected these samples and they were independent. All right, fixed and random effects. So fixed effects. So fixed has to do with the relationship between your y and your, let's put f of x, your function of x, right? So the one experiment I was thinking of is with CO2 levels and photosynthesis. Right. So let's say your photosynthetic rate is going to be equal to CO2 levels, right? So you have some beta. This is what I mean. That a fixed effect is this direct relationship, okay, for whatever plant you choose. And let's say our experiment now is going to look at high and then low levels. Okay, so what we do is, I don't know why poinsettia is stuck in my head, but let's say we're interested in CO2 levels on poinsettias. And so we get 400 poinsettias. And we're going to have, so 400, and we have 200 in the high group and 200 in the low group. Great. But we have a set of greenhouses, and each greenhouse only handles 100. Okay. And you go to some place like Penn State where they have greenhouses. They have new greenhouses and then old greenhouses. And you find that you have 4. Wait, that's a hose. So you have your greenhouses. Right. So it's low, high, low, high, and you have your samples growing in there. Okay. Now the fixed effect is how high and low CO2 affects photosynthetic rate. But these are greenhouses. And then there's idiosyncrasies. Let's say fan broken, right? So the airflow is shut down and not flowing as well. This one has, oh, Penn State, dirty windows. This one tends to overwater. And this one has humidity rates that vary. Okay, so you have these effects which they influence photosynthetic rates, but it's not part of that, the relationship between CO2 and poinsettias. And these, what plant ended up in here was at random, right? So you have your 400 plants, right? And you have some sort of randomizer. So, you pick up a plant and it, goes in greenhouse 1, 2, 3, or 4, and you just start assigning them, right? Like I can show you how to do this at R. You say 1 to 4 sample, and then you add 400. It'll give you 400 samples that are randomly select 1, 2, 3, 4. So 1, 1, 4, 3, 3, 1, 1, and so on. So the effect of greenhouse is a random effect. It's not a fixed effect. Okay. So it's subtle, but you have to recognize these differences. And if you were to do this, right, you would have what's called a mixed model, because what you have is photosynthetic rate equals CO2 levels plus the greenhouse, right? So this is random, and then this is the fixed. Okay. Other random effects might be if you have 2 people, say, taking measurements, and there's a potential where the person taking measurements is influencing the measurement, then you have to account for that. And since that's not part of the system, right? So if you're looking at CO2 and sort of concentration levels, and you're doing a survey, and you only have two people out asking people the surveys, you may account for that person, because maybe one wants to rush people and it stresses them, and the other one is more relaxed. So there may be some subtleties. So the person taking measurements, that's a random effect. Time is a random effect often, not a fixed effect, right? Which is kind of weird. But random effects also make it so you have autocorrelated measurements. So like in education, you'll see a lot of random effects mentioned, because let's say you are interested in some sort of intervention, you have some sort of study hall, and you select students at random, but then you have, so a teacher has a class of 20 students, and then you have 50 teachers, and then you randomly select students. But then if you have 2 or 3 students per teacher, there's going to be a teacher effect. And then if you have that across schools, you'll have a school effect. And then you may have a regional effect. And then some states are better supplied economically and may have like breakfast for students, so students don't go in hungry, and you have more standardized students and they're less stressed. So you could have a state effect, right? These are all random effects. So if you compare Mississippi schools versus say Connecticut schools, so the top and the bottom, you'll find that there are some fixed effects and then many, many random effects. So you may have a teacher in Mississippi that is exceptional, that brings the scores up, and a teacher in the Connecticut that brings the scores down. and it has nothing to do with the intervention per se. All right. Hopefully you were like the second kid in the dentist office, and that wasn't like pulling teeth. All right. Thanks for listening. If you have any questions, just send me an email.